Welcome to the Problemas channel Season 2 Episode 17, the episode which I have titled The Pythagorean Theorem Equated, because in this episode we will discuss my solution of the mathematical problem S2E17, in which we were asked to generate a proof of the Pythagorean theorem, also known as Euclid's Elements Book 1, Proposition 47, using the equation problem solving approach, which we have begun studying in the previous episode. Before I do that, however, as a traditional friendly reminder, if you're joining our channel mid-season, then first of all, thank you very much for your vote of confidence and welcome to our channel. And second of all, it is a good idea for you to go to the home page of this channel and in the channel's trailer section, find the episode titled The Problemas Channel How To, and watch that episode in its entirety. It's not that long. That episode is about 20 minutes or so long. Follow all the instructions given in that episode, because in that episode we explain and motivate everything that we do on this channel. In the previous episode, we explained that according to the equation problem solving approach, that is, if we want to solve this or that technical problem using an equation or a system of equations, we are to introduce as many variables as needed. Then we are to construct as many equations as possible using the variables that we just introduced. And as a third and final step, we are to solve as many equations as we can. And of course, we are to validate the result against the specific nature of the variables in the given problem. Consequently, in the mathematical problem S2E17, the battle plan for that problem is the following. First, we will introduce an auxiliary geometric object, to which we will refer as the in-circle or the inscribed circle of a given non-degenerate Euclidean right triangle. And then we will introduce a variable or an unknown that will keep track of the length of that radius or the inradius of the given right triangle. Next, we will construct several equations, and we will thus obtain the expression that will be a function of the lengths of the sides of the given right triangle that will represent the inradius in two different ways, because the inradius of any planar and non-degenerate triangle is a unique magnitude. It's one and the same. We will equate the two expressions and thus produce the identity or the equation that is sought after in this problem. In Season 1, Episode 1, we define mathematics as an art of telling a story, and in order to put that story together, we need to exhibit precisely ingenuity, creativity, and improvisational skills, because for the most part and in large in mathematics, there do not exist these predefined scripts that we can just animate, and the burden of creating that script is on us. In this problem, using our own ingenuity and creativity, we decided to introduce an auxiliary object into the mix, to which we refer as the in-circle, shown over here in yellow. And the moment we introduce that in-circle into the problem, then each and every side of the given non-degenerate planar Euclidean right triangle becomes composite. That is, the length of each such side can be represented as a sum or as a partition of two smaller line segments. That is, recall that the center of the in-circle of every non-degenerate planar Euclidean triangle is located at the intersection of the bisectors of the interior angles of the parent triangle. For example, in this case, if we agree that ACB is the given non-degenerate planar Euclidean right triangle, then the center O, or the in-center of the in-circle, will be located at the intersection of the bisectors B O, C, O, and A, O as shown in this diagram. And by definition, that point is equally distant from all three sides of the parent triangle. And again, by construction, the points E, F, D in this diagram represent the points where the sides A, B, B, C, and C, A touch the in circle shown over here. That means, in a slightly more technical language, that the points E, F, and D are the orthogonal projections of the point O on the sides A, B, B, C, and C, A correspondingly. That means that the lengths of the line segments OE, OF, and OD is one and the same. Let's record this. The length of the line segment OE equals to the length of the line segment OF equals to the length of the line segment OD. And this is our first variable that we introduce into the solution of this problem. Now, having said that, let us concentrate on these two triangles, OEB and OFB. By construction, these two triangles are right triangles precisely because the magnitudes of the angles OEB and OFB are right pi over 2 if measured in radians. We also know that by construction, the magnitudes of the interior angles of these two triangles at the vertex B is one and the same precisely because BO is the bisector of the interior angle of the parent triangle at the vertex B. In other words, by construction, we have it that the magnitude of the angle OBE is the same as the magnitude of the angle OBF. That much follows from the construction. So now we have in two planar Euclidean triangles, both of them are right, and in these two triangles, the magnitudes of the interior angles at B and at E and F correspondingly are one and the same. What does that mean? Well, now we recall the fact that the magnitudes of the interior angles in any non-degenerate planar Euclidean triangle sum to a constant real number. In our case, it doesn't really matter what is the magnitude of that real number. If we measure angles in radians, that magnitude will be pi radians. If we measure angles in degrees, that will be 180 degrees. It doesn't matter, but the point is that if the magnitudes of two angles in any triangle are already fixed in some sense and known, then the magnitude of the remaining third interior angle is already a done deal. The fate of that magnitude is sealed due to the fact mentioned above. That means that the magnitudes of the angles BOC and BOF are one and the same. I designated them right here. You guys can see them right here. So we will write down the fact that the magnitude of the angle BOC is the same as the magnitude of the angle BOF. BOE and BOF is one and the same. And now we have aggregated enough material to make the next conclusion, which is what? We see that the lengths of the sides OE and OF are one and the same. The length of the sides OB is one and the same between two triangles because that side is shared between the two triangles, and the included angle between the corresponding pairs of sides by magnitude is the same. Consequently, by side angle side, and what is the side angle side? Side angle side and side angle side. The two triangles that we're considering right now, the triangles OEB, triangles OEB, and the triangle OFB are congruent, and in congruent triangles, the lengths of the corresponding sides are one and the same, but we already established that the length of the side BO, since it's being shared, is one and the same. The lengths of the sides OE and OF are one and the same, since each of these sides represents the inradius. So the only thing that remains is that the lengths of the sides BE and BF are one and the same. So here we'll say that it follows that the length of the line segment BE is equal to the length of the line segment BF. And here, again, remember the recipe that is the equation problem solving approach. We introduce as many variables as needed. So now we throw an extra variable into the mix. We will call that magnitude x. We'll designate it on our diagram like so. This will be x, and this will be x. We'll designate an x. And now we come back to our early observations and capitalize on the fact that the length of the side BC is now composite. More technically, the point F over here partitions that line segment into two distinct parts. And partitioning means that this breakage or separation of the line segment BC with the point F is tight and has no gaps and no overlaps. And we thus can write down the following. The length BC, which is equal to A in our designations over here, is what? Is the length of the line segment BF plus the length of the line segment FC, and in our designations, that is X plus the length of the line segment FC. And we will work with this entity over here. If we write down it as follows: A equals X plus FC. It may not be evident immediately, but what is this entity called? Precisely, this entity is called an equation. Here, the length of the side A is known, X is unknown, and this entity over here is also not known, but in the next segment, we will uncover the other name for that line segment. In particular, let us now concentrate on the vertex C of the parent right triangle ACB, and in the manner that is very similar to the one that we discussed in the previous segment, we can show that the length of the line segment CF is the same as the length of the line segment CD. In other words, we can show that the distance from C to F is the same as the distance from C to D, and that is one elementary way to show basically that the length of the tangents that are constructed to a given circle from a given fixed point are the same. But we want to splice the variable r, the length of the inradius of the given right triangle, and the way we do that is as follows. Observe that the straight line OD, constructed this way, and the straight line BC both fall on one and the same straight line AC, and the angles that these straight lines form with the straight line AC are actually one and the same. In his book Elements, in book 1, proposition 28, book 1, I'll write it over here, book 1, proposition 28, this proposition right here, Euclid proves that if, in this specific case, two straight lines fall on another straight line in such a way that the external or exterior angle, for example, as this one, as Euclid refers to them, and the opposite interior angle, for example, this angle right here, are the same, if that is the case, then the two straight lines at hand are parallel. And that is exactly the case. By construction, the interior angle at C is right, and the angle, as we already looked, as we observed earlier, the angle ODC is also right. Correspondingly, all the angles of interest around the point D and around the point C, this angle, and this angle, and this angle are right. And that means precisely that the straight lines OD and BC are parallel. And what does that mean? It means that the line segment OD is parallel to the line segment FC. Likewise, we can show that the two straight lines, the straight line that passes through the points O and F, the straight line OF, and the straight line AC, two straight lines falling on the same straight line BC, also, as Euclid refers to these angles, fall on the straight line BC in such a way that, for example, the exterior angle at C, this one, is the same as opposite interior angle at F, for example, this one. That means that these two straight lines are parallel as well, and that means that the shape, let us write it down, the shape O, F, C, D, this shape right here, is what? At the minimum, that shape is parallelogram. And later on, in his elements, in book 1, proposition 34, in book 1, proposition 34, I'll underline it here. In book 1, proposition 34, Euclid proves that in parallelogrammatic areas, the lengths of the opposite sides are equal. And what do we have in our case? In our case, we have it that the length of the line segments OD and FC must be equal. Let's write it down over here. The length OD is the same as the length FC. And since the length of the line segment OD is equal to the length of the inradius of the given triangle, we can write down that that length is r. This is one of our variables. And by the same token, the length of the line segment OF, the length of the line segment OF is equal to the length of the line segment DC, let's say, DC, and that length over here is also the length of the line segment OF is equal to the length of the inradius of the triangle at hand. These two lengths equal one another and are equal to our variable r. And in general, what does that mean? It means that our parallelogram, the parallelogram OFCD at the minimum must be a rhombus. But since the angles of interest over here are right, this rhombus is actually a square in addition to being a rhombus. In other words, we remember that every rhombus is a parallelogram, but it is not the case that every parallelogram is a rhombus, and every square is a rhombus, but it is not the case that every rhombus is a square. And for example, as a short side note, for example, it is possible to see the difference between these two shapes from the perspective of the theory of groups. That is, the group of rigid symmetries of a square, I'll write it down over here, is isomorphic to the so-called dihedral group D4. And that group contains 8 elements, and these elements are the identity element or the identity transformation plus 3 rotations around the center of the square in the parent plane by pi over 2, pi, and 3 pi over 2 radians, plus four extra elements that correspond to reflections of the square in the diagonal axis of symmetry and the axis of symmetry that pass through the middles of the opposite sides. In other words, the cardinality, or the number of elements in the dihedral group. Usually, if such a dihedral group is designated with d sub n, then the cardinality of that group will be 2n. In this case, 2 times 4 is 8, for 8 elements. 3 rotations that I explained, 4 reflections in the corresponding axis of symmetry, plus 1 identity transformation. These are the elements of the group. The group operation is composition of this transformation. So there are 8 elements in that group. A rhombus that is not a square, however, also has a group of rigid symmetries associated to it, and the group of rigid symmetries of a rhombus that is not a square is isomorphic to the so-called Klein 4 group, and that Klein 4 group is designated as K sub 4 or V sub 4, depending on who you ask, V sub 4. And that group has only 4 elements: 1 identity transformation, 1 rotation about the center of the rhombus in the parent plane by pi radians in either direction, it doesn't matter. That's 2 elements, and another 2 elements correspond to the reflection of the rhombus in the short and in the long axis of symmetry. Correspondingly, these are the 4 elements in the Klein 4 group and the 4 elements in the group of rigid symmetries of a rhombus that is not a square. And in some sense, the theory of groups allows us to, for example, introduce a rather precise measure of symmetry for comparison purposes, because the number or the cardinality of the dihedral group D4, to which the group of rigid symmetries of the square is isomorphic, has 8 elements, and the cardinality of the Klein's 4 group is 4, or has 4 elements. 4 is twice less than 8. In that case, we can say that a square, for example, is twice as more symmetric as a rhombus. But this is just a side observation for those who want to study mathematics a little bit deeper. In our case, we don't really need this group theoretic material, but what that means for us is that the shape OFCD is not just a parallelogram, it's not just a rhombus, it is actually a square. And that means that all the lengths over here are the lengths of all the line segments that form that shape are of length r. Maybe let me write it down with the red or pink color over here. So we have these 2 results, and that means that if we come back to our equation that we constructed in the previous segment, then how can we rewrite it? Then we can rewrite it based on these observations as follows. A is equal to x plus r. And this is our first equation that has a very traditional form. But in this equation, how many unknowns do we have? We have 2 unknowns, the unknown x and the unknown r. Can we do anything meaningful with this equation just by itself? No, obviously not. So we need to introduce 1 more equation as prescribed by the equation problem solving approach. Remember the second step, construct as many equations as possible. And that is what we will do in the next segment. Wonderful. In the previous segment, we constructed the following equation shown over here, a linear equation in the variables x and r. Since this is 1 equation and the number of variables is 2, we, as the equation problem solving approach prescribes in the second step, construct as many equations as possible. are looking for a way to construct another equation. How do we do that? Well, in real time, different people will do different things. Here, for demonstration purposes, we will loiter around the side AC, designated with B, of the given non-degenerate planar Euclidean right triangle. And what do we see? We see that the point D, where the inner circle of the parent triangle and the side AC of the triangle touch, partitions that side of this triangle B into two distinct line segments. And that partitioning means that the division of the length of the line segment AC by the point D is tight. There are no gaps and no overlaps in the sum of these two line segments. And we can write down the following. If we designate the length of the line segment AD as shown over here with Y, then what shall we have? We will have the length AC is equal to the length of the line segment AD plus the length of the line segment DC, and that in our designations is what? Y plus R. And since we agreed that AC is just a stand-in for B, the length of the side B, that whole equation, that whole thing is equal to B. And we have our second equation. Let's write it down over here. B equal to Y plus R. This is our second equation, and this entity is precisely an equation. Remember, in the previous episode, I defined an equation as a result of a process that takes the given material that is relevant in this case, partitions it into two distinct parts, and establishes is equal to a relation between them. So here we say that B is equal to the sum Y and R. And how many equations do we have now? Two. How many variables do we have? 1, 2, and 3 are Y and X. So we still have one more variable than we have equations. It may seem that we're chasing our own tail, but luckily we are not, because how can we interpret the point A in this case? The point A in this case can be interpreted as a fixed point that is external to a fixed circle, the inner circle of the given right triangle. And through that point, two tangents are constructed to precisely that circle. And in the previous couple segments, we already proved what? With the case BE and BF and CD and CF, that the lengths of these tangents are one and the same. In other words, the distance from the point A to the point D, which we designate as Y, is the same as the distance from the point A to the point E, as we designated over here with the point Y. In other words, we can prove, just like we did it in the previous segments, that the distance from the point A to the point E is the same as the distance from the point A to the point D, and we refer to these distances as Y. But what happens now? Do we keep chasing our own tail, or this process terminates nicely and in our favor? Well, let's look at the point E, the point where the inner circle of the given triangle touches the hypotenuse AB of the given triangle, to which we refer as C. What happens over here? Well, just like the points F and D, the point E partitions the hypotenuse C into two distinct line segments. Partitioning means that the division here in this case is tight, with no gaps and no overlaps. And we can write the following relation over here as follows. The length AB, to which we refer as C, is equal to the distance from the point A to the point E, and the distance from the point E to the point B. And in our designations, the distance AE is Y, and the distance from the point E to the point B is X. So this becomes X plus Y. In other words, we have our third equation, C equal to X plus Y. This is equation number 3. So we have a sort of bonanza of equations. And now that we have 3 equations, 3 unknowns, R, Y, and X, there is hope that we can solve these equations. These equations turned out to be quite straightforward to handle. Each equation is linear in each and every of our variables. And what do we see tactically? Well, C is represented as a sum of x and y. So how do we manufacture that sum using these two equations? Well, we just add the bottom two equations together. What do we get on the left-hand side? A plus b is what we have on the left-hand side, and what do we have on the right-hand side? We have x plus y. This is our x plus y plus r plus r. Two copies of r become 2r, and xy comes from over here. And this sum is the synonym. Let me write it down more carefully. X, this is y. And that sum is a synonym for the length of the hypotenuse C. So what do we have? At the end, we have a plus b is equal to c plus 2r. And now we have one equation with one unknown r over here. And at this point, I hope that everyone will agree that as a function of the lengths of the sides of the given triangle A, B, and C, what we have now from this equation shown over here, we can write down the formula, as many people refer to it, as follows. R equals to A plus B minus C over 2. And this is our first equation that we obtained for the length of the inradius R of the given non-degenerate planar Euclidean right triangle. In the next segment, we'll construct a different representation of the length R as a function of the length of the sides of the given right triangle. And then we will equate the two expressions, and then we will see what happens. Observe that in the previous segments we came up with the relation between the length of the inradius of a non-degenerate planar Euclidean right triangle and the lengths of its sides using the idea of partitioning, amongst other things, of linear measures, or using the idea of partitioning the distances or the lengths. Now, in order to come up with an alternative relationship between the length of the inradius and the lengths of the sides of the corresponding right triangle, we will also use the idea of partitioning, along, of course, with the mechanics of the equation problem solving approach. But this time we will partition the measurements that are quadratic in nature. In other words, we will reason in terms of areas. And what can we say in this case? Well, coming back to our diagram, I took the liberty to hatch the relevant triangle so I can save you some time. But let us observe that the line segments O are OE, OF, and OD, being the radii of the in circle of a given triangle, are in highbrow language orthogonal, but in more straightforward language are perpendicular to each of the sides of the given right triangle. And what does that mean? That means that each and every such line segment can play the role of a height of the corresponding triangle. In other words, in detail, the line segment OE can play the role of a height of the triangle AOB. The line segment OF can play the role of a height of the triangle BOC, and the line segment OD can play the role of a height of the triangle COA. But now observe the magic of partitioning. It looks like our parent right triangle ACB, or to be more precise, the area of that triangle, is partitioned or subdivided tight with no gaps and no overlaps precisely by the areas of these three triangles: triangle AOB, the triangle BOC, and the triangle COA, each of which I hatched with different colors. The triangle AOB I hatched with red, the triangle BOC I hatched with yellow, and the triangle COA I hatched with blue. So hopefully you guys can see this partitioning very nicely on the diagram on your right. And how do we translate this into actionable material? Well, First of all, we write down the fact that the area, we'll designate area with the letter A, let's say, of the parent triangle ACB can be represented as a sum of the areas of the triangles AOB and the area of the triangle BOC and the area of the triangle COA. As shown over here, that is straightforward. This is a straightforward observation. Now, how do we convert that observation further into more actionable material? Well, we spell out each area in turn. The area of the parent triangle ACB in terms of the lengths of its sides A and B in a straightforward manner can be represented which way? Well, it's a half product of the lengths A and B, AB over 2, and that half product equal to the following sum. The area of the triangle AOB, which is what? R times C over 2. So it will be R times C over 2 plus the area of the triangle BOC, which is what again? R times A over 2. R times A over 2 plus the area of the triangle COA, which is what? R times B over 2. R times B over 2. Isn't that wonderful? And what do we have now? We have another equation with how many variables? Well, in this case, R is our variable. The 2's in the denominators of all the usual suspects in this equation cancel out. We multiply both sides through by 2 and cancel these guys out. And R can be nicely factored out from the entire right-hand side of this equation, and we can write down the following result. R is a product of the lengths of the sides A and B divided by the sum of the lengths of all the sides of the triangle. But we know that each and every non-degenerate planar Euclidean triangle has one and only one in circle and has one and only one in center and has one and only one in radius. The length of that in radius is one and the same. Consequently, the objects that sit on the left-hand side of these two relations shown here and here is one and the same, and that means that whatever sits on the right-hand sides of the corresponding equal signs also must be one and the same entity. Thus, we equate the right-hand side of this relation with the right-hand side of this relation as follows. A times B over A plus B plus C. And in the next segment, we will do a little bit of middle school arithmetic, and we will see where that takes us. Before we deep dive into the upcoming symbolic shuffling, I would like to remind everyone that even though the material that we're dealing with is absolutely elementary, this is not algebraic topology, this is not complex analysis, this is not the theory of groups, but still, what we're about to do is not real mathematics, where we call mathematics with the capital M. It's what we're about to do can be called at best computational calisthenics. And again, despite the fact that we're dealing with matters that are purely elementary, which I think is pretty much the only way to explain how this or that technical idea works, and then we can take it to more complicated areas. But the real mathematics in this problem was the act or the process of generating and regenerating, combining and recombining ideas of using the equation problem solving approach, the idea that we snatched out of our web of mathematical knowledge to introduce an auxiliary object known as the in-circle of a given triangle, introducing the corresponding variables, partitioning the sides of this triangle, partitioning the area. These ideas are real representatives of what mathematics is. And again, my claim is that in the future, as you percolate through your mathematical curriculum, if you're, for example, in middle school, when you go to high school, if you're in high school, you go to college, if you finish and graduate from college and move on to earn your PhD in mathematics, then the terminology of the objects that you manipulate and deal with will change. It will get progressively more and more complicated, but the essence of generating and regenerating, combining and recombining ideas will actually remain one and the same. And that is why the elementary problems that we consider on this channel, for example, can be viewed as a dress rehearsal for bigger and better things to come. In other words, if you get into a mental habit of being creative, if you get into a mental habit of improvising, showing ingenuity and creativity, you can take these skills into the grown-up mathematics just as well. So now coming back to our final journey, the last mile, so to speak, because we are the honest citizens of mathematics, we have to carry this computation through, no matter how dull and mundane it may seem. So here we, for example, do cross multiplication. We multiply 2 by the product AB, and then we multiply the sum of the lengths of the sides of our right triangle with this animal right here. So what do we have? On the, let me write this on top. So on the left hand side we'll have 2 times A times B, and on the left hand side I will take more space over here. Let us carefully write down the result. Let's just chug along and eat this thing one piece at a time. A times the sum will be A squared plus AB plus AC. So far so good. Plus, now B times the sum, A times B. Here I flip the numbers again. If you are in middle of high school, it may feel strange, but in college you will learn that changing the order of factors, it's not really that frivolous. We need to pay attention, but real numbers commute over multiplication. So B times A is the same thing as A times B. So this is what I wrote over here. And we move on. B squared plus B squared plus BC. And now we have to be careful. What will be the next operation? It will be minus, because here the length of the hypotenuse of the right triangles enters into our formula shown here with the minus sign, with the sign minus. So here we say minus. As a matter of fact, let's write it over here. Minus A times C. Again, we swap the order of factors on the fly because we are allowed to do that. Minus B times C minus C times C is C squared. And what do we observe now? Well, now we see that, for example, this product A times C and this product A times C enters into this sum with the opposite sign. So this AC and this AC cancel out. Next, this guy B times C enters into this expression with the negative sign, and B times C over here enters into the same expression with the positive sign. Cancel out. What do we see over here? Let's write down our intermediate result so we don't get completely lost. A squared plus AB plus 2AB plus the surviving term here is B squared, and gone. This remains minus C squared is what we have so far. But don't forget that we started with the product 2AB on the left hand side. Let's write it down over here. We'll do a little bit of juggling of our formulas, but we'll understand what's going on. So 2AB and 2AB on both sides cancel out. In other words, we subtract this product from both sides of the equation, and what do we have? A squared plus B squared minus C squared equals to what? Big fat 0. And again, this relation shown over here can be represented in a number of different ways, but here, just to keep it at the middle school level, we'll write it down as A squared plus B squared equals C squared. And this is precisely what was required to prove. And again, one more time, the string of symbolic shufflings, the string of symbolic manipulation that followed was not a real mathematics. The real mathematics was the process of generating ideas, which auxiliary objects to use, which variables to introduce, how to construct the equations. There is no recipe for all of this for all of these ideas and manipulations that we used in order to generate this proof. And this is precisely, hopefully, demonstrates what real mathematics is. It's a play of thought. It's the process of generating and regenerating and combining and recombining ideas. Now that we're basically fundamentally done with the problem S2E17, you can skip the next segment and go to the next challenge. But I would like to say just a few words, couple of minutes, about the Pythagorean theorem in general. This segment is for curious travelers only, as an extra for experts. If you're not interested, then feel free to skip forward to the next challenge. But as I prepare the board for the next challenge, you may listen to what I have to say about the Pythagorean theorem in general. It seems to me that in theoretical physics, for example, somehow the so-called Einstein's theory of relativity caught the eye of the public, and all sorts of people without any special training reason or try to reason about it. E equals mc squared and so on. And I don't really understand how this can be done in any meaningful way, because I know for sure firsthand that it takes several very not easy years to take yourself to a state where you can begin comprehending what the Einstein's theory of relativity has to say and what it is all about. And likewise in mathematics, for whatever reasons, it is the Pythagorean theorem that has caught the public attention. And granted, of course, that the matters that people deal with in the Pythagorean theorem is much more elementary. They do not require that much, intensive and long dedicated preparation. And as far as I know, again, always verify any information that you hear anywhere, especially these days. But to the best of my knowledge, where can I write it here? There exist more than 300 proofs of the Pythagorean theorem, and that actually brings all sorts of interesting discussions. How do we distinguish between two proofs, for example? What kind of secret sauce, if you will, present in either proof makes these two proofs different? What is the smallest amount of differences must be present in two proofs in order to consider them distinct? That's one thing. The other thing, and that's the primary reason that I wanted to give you this little bit of an idea about how mathematics works in general, is that if you go to Euclid's Elements, that is available actually online, thanks to a monumental effort of Dr. David Joyce, who made the English language translation of the Elements available free of charge on the internet. If you go here and look at the way the information is presented in Euclid's Elements, then and study the book 1, proposition 47, this is also known as the Pythagorean theorem, you'll see that Euclid comes up with a particular proof that may feel too elaborate for some people, or it may feel too elaborate to the not initiated audience. And here is why. In mathematics, and that is actually what one of several revolutionary ideas or revolutionary things that Euclid introduced in his work Elements, is the notion that no forward knowledge or no forward results can be used in the previous results. In other words, in so many words, the way modern grown-up mathematics works is that we take some initial set of axioms, then fundamental notions, ideas of how these notions can be strung together using quantifiers, if P then Q implication, and so on. And then plus definitions, of course, but then the only way in which things are supposed to work is the following. The proof of the current theorem, let's say I'll call it theorem number K, cannot contain any future knowledge or any not proved results. And in positive terms, the proof of the current theorem T sub K, for example, can only contain the proofs or references to the previously proved theorems, definitions, and axioms, and so on. And as a result of this requirement of how modern grown-up mathematics works, in theory, again, this is mostly a thought experiment. It's not very practical. I don't think anyone ever does it. But in theory, every theorem can become a node in a structure that can be called a dependency tree. In other words, here, for example, this theorem can depend on several theorems this way. For example, let's say this way, and this way, these theorems in turn can depend on other theorems in some intricate way. But the thing is that such a structure has to be a tree, and we already worked with trees a little bit in our previous episodes when we worked with coins. A tree is a graph-theoretic structure which has no cycles, and between each two nodes of which there exists precisely one path. And in order to show you how a dependency tree for a very straightforward theorem that many middle school students learn early on, the theorem that says that the sum of magnitudes of the interior angles of every planar triangle sums to pi radians or 180 degrees. That dependency tree looks as follows. Exactly. And you can see that I did not list all the dependency for example, theorems number 3 and number 8, or propositions number 3 and number 8, but you can trace them if you look on the left-hand side of the diagram that you just saw, so to give you an idea. And what that means is the following. If you are interested in generating your own proof, for example, of the Pythagorean theorem, then by all means do it. And I'm pretty sure that many people do it in any which way without being aware of the requirement that each and every theorem in grown-up and modern mathematics, in the vaguely defined layer of mathematics, has or becomes a node in the corresponding dependency tree. And the current results or the current theorem cannot depend on any future results or any results that were not proven prior. So by all means, of course, the point I'm trying to make is that by all means do try to generate all sorts of wonderful proofs of the Pythagorean theorem on your own. Exercise your wits, exercise your creativity. But at the end, if and when you decide to join the grown-up mathematics, please be cognizant of the fact that things may seem strange at first, but then you will just have to pay attention to which material you can legally use in the generation of the current proof of the theorem at hand. This is it for the solution of the problem S2E17, and we will look at the next challenge in the next segment. Wonderful. Now that we're done with the mathematical problem S2M19, our next challenge, the mathematical problem S2M20, will be the following. In this problem, you are invited to solve the following algebraic equation in the most famous variable of all time, x, a polynomial or algebraic equation in x, which looks as follows. X squared minus 5 is equal to square root of x plus 5. In words, one more time, x squared minus 5 is equal to square root of x plus 5. And by now we hope that all the members of our audience are sufficiently indoctrinated, and they all understand that in a big way and in a good way, we do not really care about the specific roots of that equation, but what we do care about is your story of how and why you did what you did in order to recover the roots of that equation. In order to give you guys a chance to solve this problem completely on your own, I will not say anything else. But for those who need a hint, The hint number one will be the following. We're still studying the mechanics of the equation problem-solving approach. Hint number two, the first step of this problem-solving approach prescribes that we introduce as many variables as needed. And a hint number three, in case you need it, is the following. The title of the episode in which I will share my solution of the problem will be the following. Now you know me, and now you don't. This is it for this episode. Good luck. Thank you for your time. Thank you for watching. I will see you in the next episode, in which I will share my solution of the mathematical problem S2E17.